Hello everyone, welcome to the April 3rd edition of Math 135. A couple reminders, your web assignment is due today, and you should remember to continue working on your project updates with your team. All group members are expected to contribute equally, and your grade is individualized to some extent. All right, so today we're going to talk about more confidence intervals because the technique is different as we investigate different statistics. So thus far, we've been mostly thinking about the sample mean, and today we're going to talk about the sample proportion. So where does the sample proportion occur? It occurs all over the place, in political polling, in opinion polling, in polling of our students here. And so we want to have some confidence that our poll is accurate, or at least how accurate is it, assuming that our sample is truly random. Anyway, before we get into all those details, let's talk about what the sample proportion is. So the main things that you are interested in are these quantities, p hat and q hat. P hat is the proportion of successes. So let's say you're interested in the proportion of Lee students who want to go outside today. So p hat is the number of students who want to go outside today, and n is the total number of students. Q hat is 1 minus p hat. These would be the students who do not want to go outside today. All right, so the margin of error is how far off is our estimate. This is an estimate. It's not the exact proportion. It's some estimate based off of our sample. The margin of error is how far off is it. So I might survey you right now, all of you watching the video, and maybe 75% of you want to go outside right now, but I didn't survey all Lee students. That's why this is an estimate of what all Lee students want to do. All right. So to construct our confidence interval, we actually have to verify two things. We didn't have to verify as much before in the case of sample mean, but now there are two conditions that really must be met. We must know that the number of participants times p hat is bigger than 5, and the number of participants times q hat must be bigger than 5. And we'll see this play out in just a little while. So if I do know that n times p hat is bigger than 5 and n times q hat is bigger than 5, then I can create the following confidence interval. And the good news is we don't need a new distribution. We get the same old z distribution from before. This is the standard normal distribution and has the same table that we were using in the past. And from that, we have a formula for the confidence interval. So let's do an example and see how this all works. All right, so let's find a confidence interval for the proportion of students at Lee from Tennessee. So normally I would do this in class, but I'm going to use data from a previous class, and then we can use that. So let's change back to our whiteboard. And we want a confidence interval. So we create a sample. And in this sample, we find that of 22 students, we have 8 of them are from Tennessee, and 14 are not from Tennessee. So I realize that my p hat is 8 over 22, and my q hat is 1 minus p hat. So that's 14 over 22. And we'll just approximate these to a few decimal places. So 8 over 22 is about 0.36. And so this is about 0.64. All right. So we need to check that n times p hat, which is 22 times 0.36, which is about 7.92. That's bigger than 5. So that hypothesis is met. And n times q hat, which is 22 times 0.64, that's about equal to 14.08. And that's also bigger than 5. So those two hypotheses are met. So now that we have those hypotheses, we can construct what we want to construct, which is a 95% confidence interval. So now we're going to construct a 95% confidence interval for the proportion of Lee students from Tennessee. All right, so our margin of error is roughly equal to our critical value times the following expression, p hat times q hat over n. So let's see if we can get that critical value up. So here's my table, and I see that the critical value for 0.95 is 1.96. So this is 1.96 times the square root of 0.36 times 0.64 over 22, which is about equal to 0.20. It's almost 0.20 on the nose. Okay, so now I'm ready to construct my confidence interval. So my confidence interval goes from p hat minus e to p hat plus e. And if I do that, I know that this is 0.36 minus 0.20 and 0.36 plus 0.20, which will give us a confidence interval of 0.16 to 0.56. So now we want the conclusion. So we are 95% confident that the proportion of Lee students from Tennessee is between 0.16 and 0.56. Does that match up with your intuition? Now, that's a really big range. I mean, this is everything from 16% to 56%. That's a giant range for a confidence interval. However, that's the best we can do with only 22 samples. So it probably matches your assumption that your experience at Lee is that probably between 16 and 56% of students are from Tennessee. And we're 95% confident of that. Now, this confidence interval we don't know whether it contains the true proportion of students from Tennessee at Lee. However, 95% of the time, this confidence interval that we've constructed will contain the true population proportion. All right, so now it's your turn. So let's do a different example. And this is an example about people's ages online and lying about age. So in 2011, so light years ago for you guys. Pew did a survey, and they sampled 799 teens. And what they found was that 49% of them reported misrepresenting their age online. So I want you to construct a 90% confidence interval for the proportion of teens who lied about their age online. All right, so pause the video and give this one a chance. All right, now that you've had that chance, p hat is clearly 0.49, and q hat is 1 minus p hat, which is 0.51. So we need to verify that n times p hat is bigger than 5. And if I calculate this, 799 times 0.49, I get roughly 391.5. 391.5, which is clearly bigger than 5. And if I do n times q hat, which is 799 times 0.51, it's roughly equal to 407.5, which is also bigger than 5. And so my hypotheses are satisfied, and now I know I can do a confidence interval. So I need to compute, well, first I need to find what the critical value is. And if I look at my table, I see that 90% confidence, 1.645. So I go back to here. This is 1.645. My margin of error, (1.645) square root of 0.49 times 0.51 over 799. Let's figure out what that's equal to. And it comes out to about 0.029. So our confidence intervals p hat minus e to p hat plus e. So that's 0.49 minus 0.029 and 0.49 plus 0.029. And so what this should give me is confidence interval from 0.461 to 0.0519. All right. Let me fix that up a little bit. 519. All right. So let's interpret it. We are 90% confident that the proportion of teens who have lied about their age online is between 0.461 and 0.519. So we're pretty confident, we're 90% confident that between 46 and 52% of all teenagers have lied about their age online at some point, in this case in the context of gaining access to a website or online service. So that might be different now. It's a different world than it was 2011. But we are confident that in 2011, between 46 and 52% of teenagers had lied about their age online at some point. So this is the process of constructing a confidence interval using proportions. We actually use the Z distribution again, even though we used the T distribution earlier for a slightly different case. All right. So the last things I want to talk about are what are the standards for confidence intervals in the media. In the media, the standard is the 95% confidence level. You will almost always see the confidence at 95%. However, they typically list the sample proportion p hat and the margin of error. So let's take a look at an example. So let me share the screen. So this is a study done by Gallup. Gallup does a lot of polling, and they looked at the academic rigor linked to alumni perceptions of college value. So what they did was in this survey, they asked people, do they agree strongly or not that they were challenged academically in college and how well it prepared them for life after college and whether it was worth the cost. So of the people who were challenged academically, 50% said that it prepared them well for life outside of college. Now, 50% may not seem that great, but it's way better than the alternative, which was 14% of people who were not challenged academically in college. Only 14% of those people felt well prepared for life after college. Of the people who were challenged academically, 75% reported feeling that their college was worth the cost. But of the people who were not challenged academically, only 30% said they strongly agreed that their education was worth the cost. This is an argument for being challenged academically in college. All right. So what you'll notice, though, is they have numbers here, but if you go to the bottom, let's see if I can find it here. Maybe it's not here. It must be on the other side. Give me 1 second. If you go to the bottom of the polling, you sometimes see a box that looks like this. It tells you how many participants there were, and it tells you the margin of error right here. So the part I've highlighted is the margin of error, E. E is 4 in this case, and the confidence level is 95%. And that's the standard you'll see in almost all polling. All right, let me know if you have any questions, and I will see you in class.